The United States Army is building a revolutionary system. It fuses every sensor, camera, satellite feed, and teammate's position into a single transparent display. This display is clipped directly to a soldier's helmet. They call it Soldier Borne Mission Command. And it might be the most radical transformation in infantry warfare since the invention of the radio itself. But here is the question nobody in the Pentagon wants to answer honestly. Can you actually give a human being omniscience without destroying their ability to think? To understand why this matters so urgently, you need to understand a concept that has quietly haunted military planners for 2 decades. They call it the last 100 meters problem. Here is what it means. The United States military has spent hundreds of billions of dollars building the most advanced intelligence apparatus in human history. Satellites that can read license plates from orbit. Drones that loiter for 36 hours streaming full-motion video. Signals intelligence platforms that intercept enemy communications in real time. Artificial intelligence systems that can correlate thousands of data points into a single coherent threat picture. All of that information flows beautifully from the strategic level down to the battalion level. Moves seamlessly through fiber optic cables, encrypted satellite links, and hardened tactical operations centers. And then it stops. Dead. It stops right at the edge of the battlefield. A 22-year-old infantry squad leader crouches behind a mud wall with 9 other soldiers. He makes life and death decisions with nothing but a handheld radio and his own 2 eyes. That is the last 100 meters. The place where the world's most expensive intelligence machine meets a soldier. He is still checking a phone-sized screen he has to pull out of his chest rig. Every second that soldier spends looking down at a device is a second he is not watching his sector. Every second he spends trying to decode a grid coordinate on a tiny map is a second his team is vulnerable. The information exists. The connection does not. And the cost of that disconnection is measured in body bags. The military tried to solve this before. They built the Integrated Visual Augmentation System, commonly known as IVAS. This is a Microsoft HoloLens derivative strapped to a soldier's head. The idea was brilliant. The execution was a catastrophe. First-generation IVAS headset weighed over 3.5 pounds. Soldiers reported severe nausea, migraines, and neck strain within minutes of wearing it during movement. The field of view was a narrow 30-degree window, roughly the equivalent of staring through a toilet paper roll. Thermal runaway in the onboard processors caused the display to fog in humid environments. The device consumed immense battery power. Soldiers needed to carry additional lithium-ion packs weighing over 2 pounds. This created a total head and neck burden that was physically unsustainable for 12-hour dismounted patrols. The soldiers hated it. Congressional committees questioned the entire program. Nearly $22 billion in projected life cycle costs hung in the balance. But the failure of IVAS did not kill the vision. It refined it. The Army realized they did not need to build a better headset. They needed to build a fundamentally different philosophy of human-machine interface. One where the technology disappears entirely, and only the information remains. That philosophy has a name now. And it changes everything about how we should think about the future of ground combat. Soldier Borne Mission Command is not a headset. That distinction matters enormously. It is a modular digital architecture that happens to include a head-mounted display as one of its output devices. The system is designed around a principle the Army calls fused digital awareness. The engineering behind it represents a genuine leap beyond anything IVAS attempted. Here is how it actually works. The SBMC platform integrates a minimum of 7 distinct sensor inputs into a single unified display layer. The clip-on thermal imaging module operates in the 8 to 14 micron long-wave infrared band. It detects human body heat at ranges exceeding 600 meters in total darkness. A low-light intensification camera amplifies ambient starlight and moonlight by a factor of roughly 50,000. This provides near-daylight visual clarity in conditions where the unaided eye sees nothing. A solid-state LiDAR rangefinder emits invisible laser pulses to calculate precise distance to any object the soldier looks at. It is accurate to plus or minus 1 meter at ranges up to 1,500 meters. An inertial measurement unit tracks the soldier's head orientation and body position at 200 Hz. It contains 3-axis accelerometers and gyroscopes. This ensures that digital overlays remain perfectly stabilized against the real world. A GPS receiver cross-referenced with an inertial navigation system provides positioning data with sub-meter accuracy in open terrain. It also maintains dead reckoning estimates in GPS-denied environments for up to 45 minutes. A digital magnetic compass provides instantaneous bearing information, and a short-range millimeter wave radar detects movement through light vegetation and thin walls at ranges up to 50 meters. All of these sensor streams feed into an onboard edge processor. This is a ruggedized chip, roughly the size of a deck of cards mounted on the soldier's plate carrier. This processor runs a real-time sensor fusion algorithm, not a simple overlay. Actual computational fusion. The system cross-references thermal signatures against LiDAR range data against radar movement detection to generate confidence-scored threat assessments. The moving heat signature at 300 meters with the LiDAR profile of a standing human triggers a specific response. It gets classified as a probable hostile dismount with an 87% confidence score. That classification appears on the soldier's display as a single red diamond icon with range, bearing, and confidence percentage. No interpretation required. No map reading. No radio call. The soldier looks at the world and the world tells him what is dangerous. Sensor fusion alone is merely clever engineering. The real revolution is what happens when that fused picture gets shared across an entire squad simultaneously. And this is where the operational reality gets genuinely terrifying for any adversary. Picture this. A 9-man infantry squad is conducting a night patrol through broken terrain. Rolling hills, scattered tree lines, a dry riverbed cutting through the center of their sector. Zero ambient light. No moon. The squad leader is moving at the center of the formation. His point man is 80 meters ahead. His rear security element is 60 meters behind. Nobody can see anyone with their naked eyes. But on every soldier's display, 9 blue chevron icons move in perfect synchronization. Each one is tagged with a name, a range, and a bearing. The squad is a single organism with 18 eyes and 1 shared brain. The point man's thermal sensor detects 3 anomalous heat signatures in a tree line 400 meters to the northeast. The system logs the detection. Amber diamond icons appear. Not red. Amber means unconfirmed. The AI classifier has compared the thermal profiles against its training library. The signatures are consistent with human body heat, but the confidence is only 61%. Could be livestock. Could be warm rocks retaining heat from the afternoon sun. Could be 3 fighters waiting in ambush. Here is where the fusion becomes decisive. The point man's LiDAR fires a burst of invisible laser pulses toward the tree line. Range confirmed, 412 meters. The radar module detects subtle lateral movement consistent with a human shifting position. This is distinctly different from the static heat radiation of a boulder. Confidence jumps. The AI reclassifies. 79%. The amber diamonds flicker. Still not red. The squad leader sees all of this on his own display in real time. He does not need the point man to call it in over the radio. He does not need to ask for a distance estimate. He already knows everything the point man's sensors know. This is because the mesh network has shared the raw data instantaneously. He makes a decision. He issues a hand signal to halt the patrol. He activates a small quadcopter drone tethered to his kit. The drone climbs to 60 meters. Its downward-facing infrared camera confirms 3 prone human figures positioned behind fallen logs. The AI identifies the elongated thermal profiles of shouldered rifles. Confidence score updates across every display simultaneously. 94%. The amber diamonds snap to red. 3 hostile dismounts. 412 meters. Bearing 047 degrees. Armed. Stationary. Probable ambush. Every soldier in the squad sees the same picture. Every soldier knows the exact location of every threat and every friendly. The squad leader drags his finger across his wrist-mounted controller and assigns sectors of fire. Each fire team's assigned sector appears as a transparent colored arc on their individual displays. He taps a pre-formatted fire support request. The system auto-populates a 9-line medevac template and a call for fire request. The grid coordinates are already filled in from the LiDAR and GPS data. In a traditional infantry engagement, building this level of shared understanding takes time. It would require 3 to 5 minutes of urgent radio traffic, risking enemy detection by signals intelligence. With Soldier Borne Mission Command, it took 11 seconds. The ambush that was supposed to catch the squad by surprise has been completely reversed. This happened before a single shot was fired. But this is where I need you to pause and consider something deeply uncomfortable. Because this technology does not just solve problems. It creates entirely new ones that we are nowhere near ready to address. Everything I just described sounds like a battlefield superpower, and it is. But the human brain was not engineered for omniscience. Neuroscience research at the Army Research Laboratory has consistently demonstrated a vital fact. Increasing the volume of visual information presented to a soldier does not automatically improve decision-making. In fact, beyond a specific threshold, it actively degrades it. Studies conducted during IVAS field trials at Fort Moore revealed a measurable increase in decision latency. Soldiers with full sensor overlays took approximately 1.4 seconds longer compared to those using minimal displays. In high-stress simulated engagements, soldiers with maximum data overlay committed more fratricide errors. They averaged 23% more errors, shooting at friendly forces due to visual clutter. Cardiac stress measurements revealed that mean heart rate increased by 11 beats per minute in soldiers using full overlay. This indicates elevated cognitive load rather than enhanced combat performance. The Army calls this the cognitive paradox of augmented warfare. More information should mean better decisions. But the human visual cortex can only process approximately 40 bits of conscious information per second. A fully activated SBMC display is pushing data at rates that exceed this biological limitation by an order of magnitude. The engineers working on this problem know it, and their solution is genuinely fascinating. Instead of showing soldiers everything, the system is designed to show them almost nothing. The default display state is what the developers call whisper mode. In whisper mode, the soldier sees only three things: friendly positions as small blue dots at the periphery of their vision, a simple heading indicator at the top of the display, and their own current grid coordinate in small text at the bottom. That is it. The world looks almost completely natural. No clutter. No data. No distraction. The system only escalates to full overlay when the AI determines that the tactical situation demands it. This is not a video game bolted onto military hardware. It is the integration of training and operations into a single seamless platform. Soldiers wear this hardware into combat and into the classroom interchangeably. The SBMC program is currently managed through the Army's Other Transaction Authority process, designed to accelerate delivery of experimental technology to the tactical edge. Elbit Systems of America holds a primary prototype contract valued at approximately $120 million, whose Alan Hamilton is developing the software backbone, including AI threat classification and extended reality tools. The system is built on a modular architecture backward compatible with the Android Tactical Assault Kit. This ensures that SBMC plugs directly into the existing digital infrastructure that soldiers already know. First operational prototypes are being evaluated now. The timeline for scaled fielding is deliberately classified, but the trajectory is unmistakable. The era of the disconnected infantryman is coming to a close. The soldier who fights with his own eyes and nothing else is ending. What replaces it is a hybrid warrior, part human intuition, part machine perception, fused together at the speed of sight. But here is what keeps me thinking long after the technical briefings end. Every piece of data flowing through that display has to travel across a network. And, on a modern battlefield, that network is the single most valuable target the enemy will try to destroy. The question is not whether sensor fusion works. It does. The question is whether the network that carries it can survive. Every electronic warfare system on the planet is trying to kill it. That is exactly what we are going to break down next time when we examine how Soldier Borne Mission Command creates a network safe zone. This invisible digital fortress protects the data your soldiers depend on to survive. And what happens when that fortress comes under direct assault?